All right, so Yara's back to help me talk through this last one because she hates logical fallacies. So this last bit, I'm just going to talk about some different logical fallacies or flaws in our thinking that can kind of trip us up and cause issues with our analysis. So a logical fallacy is just any type of flaw in our reasoning. These flaws can undermine the logic of our argument. They can be made either on purpose or by accident, and they can often be identified because of a lack of evidence to support the claims or decisions, or the evidence being presented is misleading or untrue. So a good example of a logical fallacy would be like a hasty generalization. Like, for example, somebody saying, I saw a violent protest on TV, jumping to the assumption that protesters incite violence, right? So take one data point, generalize to the whole population. It's just not how things work. So one issue could be uncertainties related to boundaries or labels. So since geographic phenomena often don't have clear natural units, we're often forced to assign zones or labels to our work. So something like census tracts. So this is a convenient way of simplifying a complex process. However, these boundaries and labels are often vague or ambiguous. They might be difficult to defend because they're arbitrary. And where to draw a boundary or what to call a zone is likely to vary significantly between people and groups. So Stats Canada has certain rules that they follow to delineate census tracts and census dissemination areas, but even the rules that they follow are quite arbitrary. And so related to that, we have data aggregation, which is an important thing to do. It's a useful tool, but at the same time, it can cause problems. So much of the data that we use to learn about society is collected in aggregate. And so what I mean by this is we take average value from many individuals within a group or an area. And so this lets us explore the average case for a group or an area. It allows us to explore the makeup or attributes of a different area or region. And it can be useful for comparing between different areas to determine where resources should be allocated, where some might be taken away. So the census is a good example of this, right? Data is collected at the individual level, but then it's aggregated at many different levels, from dissemination area on up to the national level. We're going to talk about some issues that can come from aggregated data. So one is known as the ecological fallacy. And so the ecological fallacy is just an issue related to how we interpret statistical data. When taking data collected from a group and applying that to any individual within the group, you run into serious issues. So census data is averaged for an area, and the information about an individual within that area is then lost. So you can't learn anything about individuals within groups or areas based on the aggregated data from a group or an area. So for example, the median income in 2016 for my census tract was $2,491 a month, but I don't make $2,491 a month. So, any of you could get on Simply Analytics and look at various attributes for your census tract, look at the average age or something like that. Chances are any one of those average values doesn't apply specifically to you. So you can't take a number in aggregate for a whole group and apply it to an individual. And so stemming from that, we have something called the modifiable aerial unit problem. So this is a source of statistical bias that causes big problems in GIS. So essentially, the choice of where boundaries are made and how many are used can have dramatic effects on the resulting summary values, the totals, averages, ranges. But again, all these boundaries and how many units we have are arbitrary choices. So if we use arbitrary choices to aggregate data, the values might be somewhat arbitrary. So most boundaries are made in GIS are arbitrary and modifiable, and they're just subject to the decisions of whoever is doing or did the aggregation. Yara got bored. But anyway, so how we choose to draw these boundaries has a really big impact on the values given to these aggregated areas. So this is related to the ecological fallacy. When areas are grouped together, the way you choose to group them can change the values of the groups. So for instance, if you look at this set of 9 values, we could choose to group it 2 different ways. And say they're people and the numbers represent ages. If you group them based on into 3 sets and you group them one way, you could get very similar mean values. If you group them another way, you could get very different mean values where the highest value is more than double the lowest. And so this is just a simple illustration of how the choice of boundary and aggregation method could change values. Looking at things from a more applied example, we could look at population density in British Columbia. And so if you look at census subdivisions, you can see some finer resolution detail. You can see some higher density within regions of the interior. You can see Prince George and all that, some more dense population on the island. But if you look at census divisions instead, which are a larger block group, then some of that variability is lost, right? And so the choice of boundaries and how many to use when looking at certain values impacts the way that we perceive information. And so this has very meaningful real-world consequences, and it can also be exploited to work to a certain end. So the big issue is that data is collected at a finer level of detail, but it's being combined into larger areas of lower detail. So not only are we losing information, but what information remains can be very easily manipulated based on how we choose to draw those boundaries. So we can use this property to imply things about data that aren't necessarily true. So if you look at the examples on the right, we're drawing different boundaries and we get different results. If we create equally sized grids with larger units, we can get a relatively even distribution of high and low values, but you can carefully construct a web to create a couple high valued polygons and then many low value polygons, or you could carefully construct a web to make the values more dispersed. And so this can be exploited, for instance, in order to rig an election. And so this is known as gerrymandering, the drawing of electoral districts to encourage a certain outcome from an election. And so, for instance, you could have a population that votes 60% blue and 40% red. And if you drew 5 districts one way, you could get all blue. And if you drew 5 districts another way, you could actually rig it so that you end up with 3 red and only 2 blue. And so this has been exploited in many places. It's a process called gerrymandering. So you might remember at the beginning of term, I talked about cartography being used as a tool of oppression. Well, the modifiable aerial unit problem has been exploited by those in power to suppress votes. So for instance, I'm showing you an example of Alabama's current Republican-drawn congressional district, which is heavily gerrymandered, and a hypothetical nonpartisan congressional district, which shows essentially one more Democrat and one less Republican getting elected to Congress. And so this is also known as cracking and packing, where the state or the body in charge of drawing the electoral districts is using census and voter registration information to try and force all of the or many of the Democratic voters who happen to be in Alabama, mostly Black individuals. They try and force them all into one census tract, concentrate them, and then disperse the leftovers among the other census tract or congressional districts in order to minimize the vote. And so this leads to this feedback cycle where you have institutional racism that leads to gerrymandering, which leads to voter suppression and disenfranchisement, which leads to more racist candidates, which further cements institutional racism, which leads to gerrymandering, voter suppression, and so on and so forth. And so this is a really serious problem that happens in the United States, but to a lesser extent, it also happens in Canada as well. And so another issue that we have with aggregated data that also can be highlighted using US elections is the atomistic fallacy. And so this fallacy occurs when we assume that we can combine data that's already aggregated and aggregate it again at an even higher level. So for example, if you take the average income of census tracts in Metro Vancouver, and then average that again over Metro Vancouver to try and calculate the average income, you're going to end up with the wrong value. And so this little illustration down here just highlights what I'm talking about, right? So if you take 3 groups of numbers, we'll say they're census tracts, and we average the value for each of them, and then we average those values again, you're going to get the wrong value. You have to take the average across all values rather than aggregating and then re-aggregating. And the reason this doesn't work is because we have here 3 values in a group that's contributing to this average. Here we only have 2 values in this group that's going to this average, and here we have 4 values. But then when you average all of these again, you're not accounting for the differential numbers within each of these groups. So you end up skewing your results. When the actual mean is 6.1, the mean you would get trying to average the aggregated values would be 5.4, which would underrepresent the number. And so a good example of this is the Electoral College in the United States, where it essentially washes out the actual weight of any individual's vote because it aggregates the states, which are already aggregated. So each state has its own election, which they determine the winner, and then the winner's votes go to elect the president, which is just the wrong way to do things. If you look at a cartogram based on the total number of votes instead, you see that, for instance, in the 2016 election, the actual popular vote total was overwhelmingly Democrat, but because of the Electoral College, which is based on the atomistic fallacy, we end up, with Donald Trump winning in 2016. So it's a serious issue. Other important things to consider when thinking about data relevance and logical errors are, has the data been normalized to account for confounding factors? So I've talked about data normalization a handful of times in class already, but it's a really important thing to think about when constructing a framework to look at your data. So if you don't normalize data, you can end up presenting things that really misconstrue the gravity of the situation. So I highlighted this was looking at the police violence data, and where if you don't account for the differential demographic distribution, you could end up with a map showing that white people are the majority of police killing victims, when they are far and away not the most likely to actually be victims of police killing in all but just a handful of states and provinces. So building on that, beyond just, is there a confounding factor that I might need to think about? An important question to ask is, are these data relevant to my scenario? Am I looking at the right stuff? Am I omitting something important? For instance, did we forget to consider flood probability when looking at site for a nuclear reactor? So just some questions to ask for your data. You want to ask yourself, is the data set complete? What is the age or the date that the data was created? What's the lineage of the data? What's the resolution of the data? Is it sufficient? Is it too big, too small? What's the projection, datum, coordinate system? Is it accurate or sufficient for this analysis, right? So if you're doing something that's going to involve calculations of area, you want to make sure that you reproject into an equal area projection. What's the level of precision? Does the data seem logical and consistent? Does the cartographic representation look clean? Is the data actually relevant to the project? What's the format of the data? And why was the data compiled? So what agency created it? Is this agency trustworthy? What's the reliability of the data provider? And how is the data checked? So these are just some of the things you really need to think about when considering data sets that you're going to use for a GIS project or any sort of geospatial analysis. So lastly, I just want to mention a little bit about the final exam. So the final exam is going to be asynchronous, and you're going to have a 2-day window to complete it. It's going to be June 22nd and 23rd, so right after your final project is due. And you have one timed attempt. It's going to be 4 hours long. And the exam is going to be open book, so you can use any tools at your disposal. That's Google or any of the course notes or the labs. We can reference anything we've covered in class before. So GIS itself is an open book discipline. It relies on your ability to like Google and search everything. So, I don't want to restrict you from using that. That said, it is an individual exam. You can't work on it together. So, and the questions are going to be drawn from a bank of randomized questions. So it will not be to your benefit to work on it with another person anyway. So next Tuesday for lecture, I will give you a little bit more detail in terms of like specifics about what different things are going to be on the exam. And then I'll finish up with some lecturing on more on ethics and things like that. And then on Thursday, I'll round out any of the lecture material that I wasn't able to cover on Tuesday, and then just do a pretty broad final exam review. And then we're almost done with class.